let's talk about recursion. We'll look at some theory, a little bit of code, and several examples. So a function may call another function as part of a subroutine. Many functions use results of other functions to do whatever task that they are assigned to do. For example, a function that would implement selection sort would call a find largest or find smallest function each time through the main loop. This idea of calling something or referring to something can also work with statements like English statements. We can have self-referential statements. So a sentence that refers to itself, for example, this sentence has 5 words. That's a true statement. If we read that as this sentence referring to the sentence that we're reading, it does in fact have 5 words. Another self-referential statement is this sentence does not have 5 words. And again, referring to the sentence itself, it does not have 5 words, so that is a true statement. But if we look at this sentence has 5 words in context, then it may not be a true statement. For example, what if this sentence is referring to the previous sentence? So this sentence can refer to the thing I'm pointing at, or it can refer to myself, and so there can be some differences with self-referential or statements that refer to other statements. And then, of course, the famous statement, this sentence is false. If you analyze that, well, if it's true, then it's false, and if it's false, then it's true. And so self-referential statements can sometimes lead to issues, but in other cases, self-referential statements are perfectly fine. And it's the same thing with functions. We can have self-referential functions. The function can call itself so long as certain aspects are satisfied. So if we think about the factorial is n times n minus 1 times n minus 2, all the way down till we get to times 2 times 1. And the end statement of that typically is for non-negative values. And so we have 0 factorial is defined to be 1. And so as in terms of a function calling itself, we could define, say, a Python function. Let's call it factorial since it's going to be describing the factorial. And the input is some non-negative integer n. And the idea is that n factorial is n times n minus 1 factorial. Well, what is n minus 1 factorial? Well, it's n minus 1 times n minus 2 factorial. What is n minus 2 factorial? That continues until we get all the way down to some stopping point. And the stopping point that we can get to is, we can say if n is 0, then we're going to return 1. We're going to reach that final value that we return an actual number instead of a reference. And so the n equals 0 portion is called the base case, and the other portion is the recursive case. So if n is bigger than 0, we keep making calls to the factorial function with smaller values as the input until we get down to n equals 0, and then we return the actual number 1. The base case isn't always in terms of n equals 0. The base case is whatever is appropriate to the specific situation. But for the factorial, it's appropriate to go all the way down to n equals 0. So in terms of what is happening a little bit behind the scenes, we have a program call stack that's in the background, and every time there's a function call, that is pushed onto that stack. And so when a function calls another function, the outer function, the calling function, will pause. Its context, the information relative to it, will be saved, will be pushed to the stack. The nested function, the one that was called, executes. And then the execution context is popped from the stack and the outer function can resume its duties. With recursion, there may be many nested function calls on the stack. That context with the smaller value, and then with the smaller value still, and the smaller value still. Lots of things may be pushed onto the stack. And then when we finally get to an actual value, that value comes back. That allows the previous function to resolve with a value. Then we pop the next one from the stack and it resolves with a value, and things keep resolving with values until we get the value that we were looking for with the original function call. So what happens is if you push too many things onto the stack, there's only so much memory available, and so we can reach what is called maximum recursion depth. So our system just doesn't have any more storage space to store more of these function context calls. And so the recursive approach would break at that point. There's just not enough memory to keep track of everything that we would need to keep track of. And so sometimes to improve on that so that we don't put everything on the stack, there is an idea of something called memoization, which is not memorization. This is like a memo. We take notes. And so in memoization, the idea is that we are going to remember some of our calculated values so that we don't have to recalculate values as we go further down. So we can construct things in a non-recursive way, or if we are working in a recursive way, the idea is that as we get to certain values, we record those, we save that. We'll see more details about how to implement this process, keeping track of what we have in certain ways to improve on a recursive situation. Store these values for later lookup. We may, in a simple case, just use something like a list, but typically when we care about speed and so on, we will use a hash table, which a hash table in Python is a dictionary. So we have the key value pairs, and we're able to get those values much more quickly and much more readily. And so memoization can help avoid some of those pushes to the stack. We record some information and then do a lookup on that information. And so this trade-off involves time versus space. So there's more space that we have to record values, but that means that we're saving on some of the space that we had on the stack. The time issues are always the question when we have an algorithm, time versus space. But we are able, by combining recursive ideas with remembering some data, some information, we're able to allow this recursive process to work further. We can apply it to later in the process rather than it running out of memory. So if we're looking for certain kind of recursive values, the stack depth might be exceeded, and so we're not able to continue with the process. But if we had saved some values off, that clears off some of the stack memory value locations so that we can continue further. Sometimes a lot further, sometimes a bit further, and it will depend on the context. But for this, let's just think about the idea that sometimes if we take some notes and record some data somewhere, that we're able to look back at that data in order to go forward. So we've seen the Tower of Hanoi problem. We have 3 pegs, and then we have some disks on those pegs. There are n disks on the pegs that get smaller in size, and the idea is that we want to move all of the disks from, in this case, the leftmost peg over to the rightmost peg, but we can only move one disk at a time, and we can never place a larger disk on top of a smaller disk. And so the idea is, let's move things over one at a time, never put a larger disk on top of a smaller disk, and end up with all the disks over on the right-hand side in the appropriate order. All right, in that situation, we solve the problem by moving the n-1 smallest disks over to the middle peg. Now, that takes a lot of moves to do that, maybe, but we move the n-1 disks over to the middle peg, so we kind of pretend like that's the final peg, and then we move the biggest disk over to the rightmost peg, and then we go through the whole process of moving those n-1 from the middle to the right. And so the solution to the problem becomes, to solve the case of n, let's solve the case of n-1 in a slightly modified version. Instead of moving those n-1 to the far right, we move them to the middle. Then we move the big one over, and then we solve the n-1 task again, move from the middle to the far right. Well, how do we move the n-1 to the middle? Well, we do that by moving n-2 of them to the right. How do we get n-2 of them to the right? We see there's this repetitive call, this recursive process taking place. We keep solving the particular task by solving the smaller version of that task. So in terms of what happened in that process, if there were no disks, it takes no steps. So T of n is the number of steps it takes to solve the Tower of Hanoi when there are n disks. If there are no disks, it takes 0 steps. If there's just one disk, you just move it over. But if there are more disks, then what happens is we will solve the n-1 problem once, then we move the big disk over, and then we solve the n-1 problem again. So how long does that take? 2 times the number of steps to solve the n-1 problem, plus 1 for moving the big disk over. And notice that there's really a little bit of repetition here. We don't really need the 1 when n equals 1, because we could combine both of these steps, these last two, into the recursive step, because the value of 1 comes from that starting position with 0. 2 times 0 plus 1 gives the value of 1. So that part is really redundant to talk about what happens when n equals 1. We could just say the number of steps is 0 when n is 0, and if n is greater than or equal to 1, then apply this recursive count here. So how many moves does it require? If you have no disks, it's no moves. 1 disk is 1 move. 2 disks is 3. 3 disks is 7, and so on. And it turns out that we can see a pattern to that, and there is a closed form equation then for counting this. Rather than the count being recursive, we can write this in a closed form way. Now, the count being closed form does not tell you how to do the process. The recursive steps could be implemented in a way that it tells you exactly what you need to move where and when. But the closed form equation here just gives the count of how many steps does it take and doesn't tell you how to do the process. And you can see the pattern maybe 0, 1, 3, 7, 15, 31, and so on, that this is 2 to the nth power and then minus 1. And so there are mathematical ways to begin with a recursive description of a value and be able to modify that to determine a closed form equation, at least in lots of situations. In some cases, these recurrence relations are difficult to solve, and so we may not always be able to figure out what a closed form equation would look like. But in this particular case, we can see the connection between the two. There are other easily described recursive scenarios. The Fibonacci numbers. We're not going to go into the details about the Fibonacci numbers in terms of the history and so on at this point, but you may have seen some of the history in other places that the idea began with counting how many rabbits you would have after a particular period of time. If you start with rabbits that need some time to mature before they start producing offspring, the number of pairs of rabbits that you would have over time is one thing described by the Fibonacci numbers. There's lots of other settings that the Fibonacci numbers appear in. We care about the recursive aspect of the procedure. And so the Fibonacci numbers can be defined to be 0 if n is 0, 1 if n is 1, and then after that you just add the previous two values together to get the next Fibonacci number. Now in this case we do need a two-part base case because the Fibonacci numbers are based on the two previous values. So we can't look back two values if we don't know the first two values in the process. And so the Fibonacci numbers start 0, 1, and then you add those two together to get 1, and then the previous two, which is the 1 and the 1, to get 2 and 3 and 5, 8, 13, and so on. And this sequence continues on forever. It turns out that because of the structure of this, there is also a closed form solution to the Fibonacci numbers. The closed form equation for calculating the nth Fibonacci number involves the square root of 5. It involves 1 plus the square root of 5 over 2. You may have heard of the golden ratio before. That's the golden ratio appearing in the Fibonacci number closed form equation. How you come up with this equation, again, follows from the same kind of techniques that the previous closed form equation was developed for the Tower of Hanoi. But at this point, just knowing that there is a closed form equation that corresponds is the important part. So there's a recursive solution, there's a closed form equation. They both mathematically are equivalent, but computationally they may not be the same. On one hand, with the recursive part, we have to possibly be concerned about a recursive depth. We have the closed form equation has 1 divided by the square root of 5. It has other square roots of 5 involved. We could run into floating point issues with the closed form equation. So mathematically, they're exactly equivalent. In real life and implementation, we may see different things happening. I just saw a joke a couple of days ago talking about the Fibonacci numbers. And lots of times people will forget, is it 2 B's, is it 2 N's, is it 2 C's? What happens if we look at the consonants on the inside of the Fibonacci numbers? Which ones, how often do they appear? Well, the letters are B, N, and C, so how often do they appear? They appear 1, 1, 2 on the inside of the words. So what happens? In a way, Fibonacci is self-referential if we're counting how many times the interior consonants show up. All right, so Fibonacci numbers have that specific definition. There's another kind of number that's similar in spirit called the Lucca numbers. And the Lucca numbers are defined almost just like the Fibonacci numbers, except the base cases are different. And not both base cases, but just the starting value, n equals 0. Instead of starting at 0, it starts at 2. And so that sequence begins 2, 1, and then it goes 3, 4, 7, 11, 18, and it follows a Fibonacci-like process. Turns out this sequence also has a closed form equation that will describe its values. And in this case, we're again seeing the golden ratio in there, but we don't have that dividing by the square root of 5. And so this particular starting point has a close connection to the Fibonacci numbers, which is the reason that particular starting point has a name like this. But we could have other starting points. Instead of 2 and 1 as the starting values, we could pick other values. Whatever we like, actually, would be permissible. It's just that some of those sequences are nice and some of those sequences aren't so nice. And by nice, I mean usually there's some kind of properties or some kind of applications that come from particular starting points. The Pell numbers are defined in a similar way. They have the same base case as the Fibonacci numbers. The difference is rather than just adding the two previous values together, you have 2 times the previous value plus the 1 before that. And so to calculate the next Pell number, you look back 2 spaces again, but one of those you double, and that gives you a different set of values. This sequence begins 0, 1, that's the default portion, and then it goes 2, 5, 12, 29, and a bunch of other values. And so this pattern is just as easily described in a recursive way as the Fibonacci or the others, but it is probably a little more difficult for people to recognize the pattern that's happening in the Pell numbers. But again, there are lots of applications and uses and ways that we'll see that the Pell numbers show up in different ways. There is also a closed form equation for the Pell numbers, and the closed form equation here involves a square root of 2 in the calculations rather than a square root of 5. And so we have, again, this closed form solution that will describe the nth Pell number. We look at these kind of two-part problems or descriptions that go back 2 spaces. So there could be a more general version of that that says, okay, we have our 2 starting values, R and S, whatever they happen to be. And then rather than just adding the 2 previous pieces together, we could have some number times one of them plus some other number, or even the same number again times the other one. So we could have the idea of Fibonacci, the idea of the Lucca numbers, the idea of the Pell numbers, but slightly more general. And then even more general than that, we could look back more than 2, or we could skip some of them. You go back to previous values in the sequence to be able to extend to get the next values. This sequence would begin R, then S. The next value would be A times S plus B times R, because we go back 1 and then go back 2. And so this sequence has properties as well, depends on the R and the S and the A and B choices that we make. And so there is a way to describe what closed form solutions would look like for this, but that's kind of outside our focus right now. The idea is that lots of things can be described in a recursive way. Another recursive function that was created in terms of some early work on limits of computation and some things related to AI, McCarty's function is defined to be, we'll call it n because it's named after a man named John McCarty. So m of n again being the input value. If n is over 100, we get back n minus 10. So that's just as a specific value. This is kind of defined in this piecewise way. In the situation when n is not greater than 100, then the value is m of n plus 11. So we're going to calculate n plus 11, put that into the function m, and then take that value and put it into the function m to see what comes out. All right, so if we looked at something like m of 105, 105 is bigger than 100, and so we just subtract 10, and the output is 95. First row, nice and easy, a linear function. If we look at m of 100, though, m of 100 says, okay, now we have to put in 100 plus 11, so we're looking at m of 111, but then we need m of that. Well, m of 111, that's bigger than 100. We subtract 10. Means that we're looking at m of 101. And m of 101, we subtract 10 again, is 91. So m of 100 is 91. And that goes through this multi-step process of doing this calculation. And if you think about what happens, we are calculating, and then we say, oh, I have to calculate something else, oh, I have to calculate something else, oh, and eventually get to a point where we can get the final number and get that value back. If we went to 99, m of 99 is m of 99 plus 11, which is m of 110. All right, but m of 110 is 100, so m of 99 is the same as m of 100. Now, we could, if we had not calculated m of 100 already, we would go through the process and keep going to get to the value. But we have it written down right above there, so we use this memoization process and look back there and say, oh, okay, well, m of 99 is also 91. All right, and so you're going to get a chance to explore, think about McCarty's function, see what happens. I just used some examples of positive integers. We don't necessarily have to have positive integer inputs, so we can analyze what happens when we put other values in there. Let's look at a function called the Ackermann function. This function was developed around 1928. People were studying the limitations of computation. This limitation of computation was in terms of what can be calculated. This predates like electronic computers, but the ideas of what could you calculate with specific tools available was already being considered before the first modern computers were developed. The Ackermann function is not really the Ackermann function. There were several functions that were described at that point. The ideas are related, they're similar. This particular version we're going to look at has two parameters, non-negative integers, m and n. They could be 0, but not negative. And the idea of this specific one is often called the Ackermann function, although, again, there are several things that fit into this category. So this function is defined in multiple steps. We have this function, we're calling it a. The inputs are m and n. If the m is 0 and the n is whatever it is, then the output is just n plus 1. So that's an easy, straightforward calculation. We just look at the second entry and add 1 to whatever it is, and that's the output from the function. This is a base case scenario. Well, if the right-hand entry, if the n input is 0, then what happens is whatever the m was is decreased by 1, but then the n value is increased by 1. So the gets smaller, but the n does get bigger. And then in general, with two numbers, what's going to happen is we're going to have a more complicated response. We're going to have a of these two values is going to be a of. The first entry is decreased by 1, and the second entry is replaced by another function call. And in the other function call, the original left-hand parameter value stays the same, and the one on the right goes down by 1. So in this mixed result here, the goes down on this part, and on the other part, the n goes down. So let's take a look at some examples, some actual numerical examples to see how this function will work. So if we had, say, a of 0, 6, well, that fits the first row, and all we do is add 1 to the second entry, and we have a of 0, 6 is 7. Straightforward calculation, no additional function calls. If we look at a of 1, 0, a of 1, 0 becomes this, or calls this second row. 1, 0 is a of, okay, the first value goes down by 1, the second value goes up by 1, and so a of 1, 0 is the same thing as a of 0, 1. And a of 0, 1 now goes back to the first row, and that gives us back 2. So a of 1, 0 is equal to a of 0, 1. By the first row, that value is 2, which then returns to this one. Okay, they're all equal to 2. Now let's go to a next value. Let's look at a of 2, 0. This one's going to get a little more complicated in a moment. We'll get into the third row. So a of 2, 0 is second row call. The 2 is decreased to a 1. The 0 is increased to a 1. So a of 2, 0 is the same as a of 1, 1. And now we're in the third row. So what happens? The 1 is decreased to a 0. So we have a of 0. And then the second part is going to be replaced with this other function call again. So what is it? We have a of the original input value, that's a 1, and then the other input value, the n, is decreased. So it's 1 goes down to 0. So we have a of then all of this situation. Well, the a of 1, 0 we just calculated was 2, so this becomes a of 0, 2. And a of 0, 2 fits into the first row, and that output is 3. All right, so this can get more complicated. If we go a little bit further, let's take a look at a of 3, 0. Following our steps there, we see that a of 3, 0 will be a of 2, 1, because the first value decreases, but the second value goes up. Following our steps a little further, the 2 decreases, but then the right-hand side has the same value 2, but the 1 goes down. At this point, we notice that a of 2, 0 shows up. So we can remember what we just calculated. A of 2, 0, we just calculated that. We know what that is. And so this now becomes a of 1, 3. Well, a of 1, 3, we don't know what that one is, but we know what the rule says to do. The first value is decreased, and the second value becomes the same elm, and the 3 gets reduced to 2. But we're stuck because we don't know what a of 1, 2 is. So we're going to come down here and try to calculate a of 1, 2. All right, we apply the third rule and we get this. And we have another situation with a of 1, 1. We don't know what that one is. We come down here to calculate a of 1, 1. A of 1, 1. Apply the third rule. And we see something that we've already calculated. We have the memoization process to our advantage again. And so that value is 2, and a of 1, 1 becomes 3. All right, so now we know that a of 1, 1 is 3. Going back up a level, that means that a of 1, 2 is the same as a of 0, 3. But we know what a of 0, 3 is because the first rule says that's 4. So now we can go back up to here. This is all things that have been on our stack of, we had to stop for a little while until we got other values. Now we come back up here and we're looking at a of 0, 4, and a of 0, 4 we can calculate is 5. So we noticed that we had to go as far as we could for a little while and then stop to do something else and then stop to do something else, and then that answer comes back and that helps, and then keep working our way back toward the original. So a of 3, 0 takes lots of steps to calculate the number 5. So what happens with larger elm and n? You can guess that the number of steps will go up considerably. But not only do the number of steps go up considerably, the size of the numbers involved will get rather large. We might ask if the process always terminates. So think about what happens. So far, all of our starting values did eventually terminate. Will that always happen? And how do we know that will always happen? I'm giving it away partially. Yes, it will always terminate. At least theoretically, we may run out of time for large values and so on. But how do we know that this process is going to terminate? So think about the definition and see if you can figure out how we know that it will not just continue on forever. Think about what happens in the different function calls when elm and n get changed. What is happening? How do we know that that's always working toward a termination point? And then again, how big do these values get? We're not going to spend much time to look very far at this point, but these numbers can get very big very, very quickly. All right, so kind of as a summary, what have we seen? There are some problems that recursion can be helpful in terms of describing a solution to a process that involves iteratively solving smaller versions of the same problem, or always looking back at the same portion to continue moving forward. So when there's a repetitive process that involves smaller versions of the same task, recursion is often a useful tool. What it can do is it provides a nice mathematical description of the problem at hand, and then we can often implement that with very simple code, maybe very little code. The problem becomes that the depth and the runtime can become much too large. And so Being able to describe a problem recursively is sometimes nice for understanding purposes. Sometimes it's nice for solving small examples, but it does have limitations. And so if we use the memoization process, then maybe that can overcome some of those limitations, maybe not all of them, but will help us to be able to solve certain problems a little bit easier. And then in situations where even if a mathematically closed form solution does exist, there still may be computational difficulties. And so sometimes a recursive approach, or again, other approaches that we'll see later, might need to be used even when there is a nice mathematical solution to a problem. The mathematical solution might not be as helpful in real life situations. It turns out that some problems are just really, really hard. Now, when we say they're hard, it doesn't necessarily mean computationally or conceptually difficult, but rather that computationally they are difficult. That the amount of time required to solve that problem is just more time than we have available. Or maybe it's more memory is required than we have available. So as we move forward, we're going to talk about problems being hard, and the idea is not necessarily conceptual, but sometimes it is. So we will formalize and give a clear definition of what it means for a computational problem to be hard. So, as usual, feel free to ask questions. You can ask questions in the comments, by email, or on Discord, and have a great day.